In this video, we're going to focus on writing net ionic equations for double replacement reactions like precipitation reactions, acid-base reactions, gas evolution reactions, and also single replacement reactions. So let's begin. Let's say if you have an aqueous solution of magnesium chloride and silver nitrate. What are the products of this reaction? Now, the first thing you need to determine is if you have a single replacement or a double replacement reaction. Now, we have a reaction that's in the form AB plus CD. This is a double replacement reaction. Magnesium is like A, chlorine is like B, Ag is the C part, and D is the nitrate. So in this reaction, A is going to pair up with D to form AD, and BC are going to pair up to form CD. So let's apply this information to the problem that we're trying to solve. Now, it might be helpful for you to know the ions and their charges. Magnesium is going to pair up with the nitrate ion, and magnesium has a +2 charge. It's found in the second group of the periodic table. Nitrate is a polyatomic ion that you need to know. Using the crisscross method, we can write the formula of magnesium nitrate. So the 1 is going to go on the left side and the 2 is going to go on the right side. Whenever you have multiple polyatomic ions, you need to enclose it inside a parentheses. So one of the products will be magnesium nitrate, MgNO3 2. Now the other product, we need to pair up Ag with Cl. Ag has a +1 charge, and chloride has a -1 charge. If the charges are the same, you could just simply write them together. So this is going to be AgCl. So now, what we need to do is write the phases of every substance that we have. Now we know the first two reactants are in the aqueous phase. Magnesium chloride is soluble, and nitrates are always soluble. So magnesium nitrate is soluble as well. Now silver chloride is insoluble. It doesn't dissolve in water. And to figure this out, you need to be aware of the solubility rules. Chlorides, bromide, and iodide are generally soluble except with Ag+, Pb2+, and mercury 2+, the diatomic mercury ion. So knowing the rules will help you to determine that silver chloride is insoluble, and so it's the precipitate of the reaction. So we have a precipitation reaction. Now the next thing we need to do is balance the equation. So we have 2 nitrates on the right side. We need to put a 2 in front of AgNO3, and we have 2 chlorine atoms on the left side. So we need a 2 in front of AgCl. And now the reaction is balanced. Now the next thing we need to do is write the total ionic equation. So everything that's in the aqueous phase, we need to separate it into ions. So we're going to have the Mg2+ ion, and we're going to have 2 chloride ions. All of the ions are in the aqueous phase, by the way. Ag has a plus charge, and we have 2 nitrate ions. So that's on the left side. And then on the right side, we can only separate magnesium nitrate. Silver chloride is a solid, so we can't separate that. So on the right side, we have Mg2+. We still have 2 nitrate ions. And we have AgCl as well. And that's a solid. So the next thing we need to do is eliminate the spectator ions. The spectator ions are those that are found exactly the same on both sides of the reaction in the total ionic equation. So the nitrate ions are spectator ions. They look exactly the same. And the same is true for the Mg2+ ions. So notice that what we have left, the coefficient is a 2. This should be a 2 here. So we can divide each of those numbers by 2. So our final answer, what remains is the net ionic equation. So it's going to be Ag+, which is in the aqueous phase plus Cl minus aqueous. Aqueous just means that it's dissolved in water, and this yields solid silver chloride. Silver chloride is a white precipitate, and so that's the net ionic equation for this particular problem. So now let's try an acid-base reaction. So what's going to happen if sulfuric acid reacts with aqueous sodium hydroxide? So almost all acids dissolve in water. I don't know of any that don't. So we can write aqueous for an acid. And anytime you have a group 1 metal cation like sodium, lithium, potassium, it's always soluble. So acid-base reactions are usually double replacement reactions. So we can pair up the first and the last ions together. So we have H plus and OH minus. These two, when they get together, they will always form water. And water is a liquid. Now, the two in the middle, Na and SO4, we can pair those. Sodium is in group 1, so it's going to have a +1 charge. Sulfate is a polyatomic ion that you should commit to memory, and it has a -2 charge. And so using the crisscross method, it's going to be Na2SO4 1. But if it's a 1, you don't got to write it. So the other product is sodium sulfate, Na2SO4. And we said that alkali metals are always soluble, so sodium sulfate is a soluble substance. So we're going to write AQ for the phase. And now the next thing we need to do is balance the reaction. So we have 2 sodium atoms on the right side, so we need to put a 2 in front of NaOH. Now notice that we have 2 hydrogen ions, 2 hydroxide ions. That's going to make 2 water molecules. So let's put a 2 in front of H2O. And at this point, the reaction is balanced. So our next step is to write the total ionic equation. So every substance that is in the aqueous phase, let's separate it into ions. So H2SO4 can be broken into 2 H plus ions and 1 sulfate ion. Sodium hydroxide, it's Na plus and OH minus. But there's a 2 in front of it, so we have to incorporate that. Now water is a liquid, so we're not going to separate it into ions. Keep in mind, all of the ions, they're in the aqueous phase, so you can write AQ if you want. Sodium sulfate, it's aqueous, so we need to separate it into ions. So now, what are the spectator ions? Do you see which ions are spectator ions? Feel free to pause the video and cancel the spectator ions. So these are the ions that are exactly the same on both sides. Sodium is a spectator ion and sulfate. Now, what remains, we're going to divide the coefficient by 2 because they're all even. So the net ionic equation for this reaction, and pretty much for almost any strong acid, strong base reaction, it's H plus OH minus yields water. This is the usual net ionic equation for an acid-base reaction if the other substance is soluble. So this is the answer for this particular problem. What about if we react a weak acid with a strong base, like KOH, and they're both aqueous? How is this one different than the last one? Feel free to pause the video and try this example yourself. So we know that H and OH are going to pair up, and these two will always form water. Now what about the two in the middle, potassium and fluoride? Potassium, it's a group 1 alkali metal, and so it has a +1 charge. And fluoride is a halogen that has a -1 charge. Because the charges are the same, you can simply write them together. And potassium is always soluble, so let's write out aqueous. Now it turns out that we don't need to balance the reaction, it's already balanced. But what we do need to do is write the total ionic equation. And it's something that you need to keep in mind. HF is a weak acid. H2SO4 was a strong acid. For weak acids, they don't ionize completely, even though they do dissolve in water. So this is the one case where you might have a substance that's aqueous, but you shouldn't separate it into ions. So we're going to leave HF the way it is because it's a weak acid. KOH is a strong base. It ionizes completely. So we're going to separate it into individual ions because that's what happens when it's mixed with water. It completely dissociates. Water is a liquid, so we're not going to change that. And potassium fluoride, we can separate it into ions, into a K plus and F minus. So what are the spectator ions in this particular problem? So potassium is exactly the same. So the final net ionic equation is HF plus hydroxide, which yields water and fluoride. So everything is going to be in the aqueous phase except liquid water. And so this is the net ionic equation for this example. Now, let's go over a gas evolution reaction. So let's say if we have aqueous sodium carbonate and hydrochloric acid, which is also aqueous. What are the products of this reaction? So we can pair up the first and the last because it's a double replacement reaction. Sodium has a +1 charge, and the halogens like chloride, fluoride, they're going to have a -1 charge. And because the charges are the same, we can simply write them together. Sodium chloride is soluble. Alkali metals are always soluble. It might be wise to briefly review the solubility rules. So now what about when we pair up H and CO3? What's going to happen? H has a +1 charge, and carbonate has a 2- charge. So if we pair these two together, it's going to be H2CO3, carbonic acid. However, carbonic acid, you need to know that it breaks down into water and CO2. So water is a liquid and CO2 is a gas. So that's why this is called a gas evolution reaction. So now the reaction is already balanced. So let's go ahead and write the total ionic equation. So let's separate sodium carbonate into ions. So we have 2 Na plus cations and carbonate. HCl, we can separate that into H plus. Well, to balance it, we do need to put a 2 in front of HCl, and we do need a 2 in front of NaCl. So it turns out it wasn't balanced. So we have 2 H plus ions and 2 chloride ions. And this is going to yield 2 Na plus ions, 2 chloride ions. Water is a liquid, so it's going to stay the same. And carbon dioxide is a gas, so that is going to remain the same as well. So we could eliminate the sodium ions and we could eliminate the chloride ions. So what we have left over is the net ionic equation, which is 2H plus aqueous and the carbonate ion aqueous, and this is going to produce liquid water and gaseous carbon dioxide. So this is the net ionic equation for this particular reaction. Now, before we go into our next example, let's briefly review the solubility rules. Ions that are always soluble are the alkali metals like sodium, potassium, lithium. Ammonium is always soluble. Nitrates, acetates. If you see these ions, for the most part, they're always soluble. Now, the ions that are generally soluble will be on the left side, and the exceptions will be on the right side. So, the ones that are generally soluble are the halides, like chloride, bromide, and iodide. Now, they're generally soluble except when bonded to one of these metal cations, like the lead 2 plus ion, silver, which we covered that one already, and the diatomic mercury 2 plus cation. Now, sulfates are generally soluble except when bonded to like elements like calcium, lead, barium, strontium, to name a few. And each of these have +2 charges. Now, you need to know the ones that are generally insoluble. Now, if they're attached to one of the exceptions, they're going to be soluble. But without the exception, for the most part, it's insoluble. So, hydroxides are generally insoluble, except when bonded to group 1 metal cations like sodium, lithium, or potassium, or even the ammonium ion. That's the only time they're going to be soluble. And also some of the group 2 metals like calcium, barium, and strontium, but not magnesium. Magnesium hydroxide is insoluble, but calcium hydroxide, it's somewhat soluble, and strontium and barium hydroxide are soluble. Now, the other ones that are insoluble are the carbonates, sulfide, phosphate, and chromate. The exception to this is the alkaline metals, the group 1 metals, or the group 1 metal cations. Sodium, lithium, potassium, and any other element that's in that column. So now let's go over another gas evolution reaction. So what's going to happen if ammonium chloride reacts with strontium hydroxide? So feel free to pause the video, predict the products, balance the equation, and then write the net ionic equation. So ammonium chloride, is that soluble or insoluble? Ammonium is always soluble, so this has to be aqueous. Hydroxides are generally insoluble, but strontium is a heavy group 2 metal, and hydroxides are soluble for heavy group 2 metals like strontium, barium, and calcium. Now, ammonium is going to pair up with hydroxide. So we have ammonium, which is NH4 plus, and hydroxide, which has a -1 charge. So we could simply write this together as NH4OH. Whenever you have NH4OH, this can break down into NH3 and H2O. Another way you can see NH4 plus can dissociate into NH3 and H plus. And so hydroxide reacts with H plus to form water, and the NH3, you can see it just stays as NH3. So whenever you get NH4OH as a product, know that it's going to break down into ammonia gas and liquid water. And you simply just have to know that. Now for the last compound, we need to pair up strontium and chloride. Because strontium is in group 2, it has a +2 charge, and chloride has a -1 charge. So when we pair these two together, it's going to be SR1Cl2. And chlorides are generally soluble except with silver, lead, and mercury, so strontium is not an exception, so this is going to be aqueous. So let's make sure that the reaction is balanced, and it's not. So let's put a 2 in front of NH4Cl, which means we need 2 NH3s, and we need a 2 in front of H2O. And so now the reaction is balanced. So now let's write the total ionic equation. So we have 2 NH4 plus ions on the left side, 2 chloride ions on the right side. On the left. We have Sr2 plus and 2 hydroxide ions on the left side. Now on the right side, ammonia is a gas, so we're going to keep it that way. Water is a liquid, so we can't change that. Now strontium chloride, we can write it as Sr2 plus, and the chloride will leave it as 2Cl minus. So chloride will be eliminated and strontium will be eliminated as well. So the net ionic equation for this reaction is going to be 2NH4 plus aqueous and 2 hydroxide ions aqueous, and this is going to produce 2 NH3 gas molecules, which is ammonia, and 2 liquid water molecules. Now granted, all of the coefficients are 2, so we can divide everything by 2, and so it's just going to be NH4 plus hydroxide yields NH3 and liquid water. And so that's going to be the final net ionic equation. Now, before we jump into single replacement reactions, you need to be familiar with the activity series. So in the activity series, alkali metals like lithium are very reactive, and then you have like alkaline earth metals like magnesium, then aluminum, and then zinc, Fe, nickel, hydrogen, copper, silver, and gold. So the reactivity increases as you go this way for the metals. For the nonmetals, you have fluorine, chlorine, bromine, and iodine. Fluorine is the most reactive nonmetal. So magnesium metal can easily displace zinc metal out of the solution, but zinc metal cannot displace magnesium. And the reason why you need to know this is so you know if the reaction is going to work or not. Fluorine can easily displace bromide out of the solution, but iodide cannot displace chloride. So you need to know which one is more reactive and which one is less, and how they can work or not. So the element that's more reactive can displace the less reactive element out of the solution. So let's go over an example. So let's say if we have, oh by the way, the general equation for a single replacement reaction looks like this. It's like A plus BC turns into AC plus B. That's the general equation for the single replacement reaction. So let's go over an example. So let's use aluminum metal, which is a solid, and let's react it with an aqueous solution of copper chloride. So aluminum is like all the way over here, and when we wrote the activity series, and copper is on the right side. So aluminum is more reactive than copper. If you go to Google Images and type in the activity series, you'll see that aluminum is above copper, which means that aluminum is strong enough to displace copper out of the aqueous solution. So this reaction can work. So let's go ahead and predict the products, and let's balance the equation, and then we'll write the net ionic equation. So aluminum displaces copper, so we're going to have copper solid, and as it displaces copper, aluminum is going to pair up with the chloride ion. Aluminum has a +3 charge. It's in group 3A of the periodic table. Chloride has a -1 charge. So if we pair these two together, we can see that the other compound is going to be Al1, which we don't need to write, and then Cl3, which we do need to write. Now, aluminum chloride, is it soluble or insoluble? As we said, chlorides are generally soluble except with silver, lead, and mercury. So because aluminum is not an exception, this is going to be aqueous. So now let's balance the reaction. Notice that we have 3 chloride ions on the right side, 2 on the left. The least common multiple of 2 and 3 is 6. So what that means is that we need a 2 in front of AlCl3. So we'll have 6 chloride ions on the right side. And we need a 3 in front of CuCl2, so we could have 6 chloride ions on the left side. And so the chloride ions are balanced. Now, notice that we have 3 copper atoms on the left. We need to put a 3 in front of Cu. And we have 2 aluminum ions on the right side, so we need a 2 in front of Al. So it looks like everything is balanced. Let's go ahead and write the total ionic equation. So the aluminum solid is going to stay the same. Copper chloride, we can write that as 3 copper 2 plus ions, and 3 times 2 is 6, so we're going to have 6 chloride ions. And on the right side, copper is a solid, so we can't change it. Aluminum is going to be plus 3, and we still have 6 chloride ions as well. So notice that the spectator ions are the chloride ions. And so for the net ionic equation, it's going to be 2Al solid plus 3Cu 2 plus aqueous, which turns into 3Cu, or 3 solid copper atoms, plus the aluminum 3 plus cation, which is in the aqueous phase. And so this is the net ionic equation for this particular single replacement reaction. Now, let's say if we have this reaction, nickel metal reacts with iron sulfate in a single replacement reaction. So the first thing you should do before you should even write the products is determine if this will work. If you go to Google Images and look up the activity series, you'll see that iron is above nickel. So nickel metal cannot displace iron out of the solution because nickel is below iron metal. In the one that we wrote, we had aluminum, zinc, Fe, nickel. So Fe is more reactive than nickel, which means nickel metal cannot displace Fe out of the solution. So here we're going to have no reaction. Now what about this one? So let's say if chlorine gas reacts with an aqueous solution of sodium bromide. What are the products of this reaction? And how would you write the net ionic equation? So chlorine, which is a nonmetal, it's going to replace another nonmetal, bromide. And as it displaces bromide out of the solution, it's going to pair up with Na. But we need to see if chlorine is even strong enough. So we know that fluorine is more reactive than chlorine, which is more reactive than bromine, and that's more reactive than iodine. This one's easy to remember because it follows the periodic table. As you can see, nonmetal reactivity increases towards fluorine because fluorine is the most electronegative element out there. So chlorine is more reactive than bromine. Chlorine is strong enough to displace bromide out of the solution. And so that's what you need to know for this particular problem. And so you need to know how to use the activity series to determine if the reaction is going to work. And this one is. So if if chlorine kicks out bromide, that means chlorine is going to pair up with the sodium ion. Sodium has a +1 charge, and chloride has a -1 charge. Since the charges are the same, we can just write them together as NaCl. Now bromide is going to be oxidized to bromine, and so it's going to be Br2. And bromine is a red liquid. Sodium chloride is soluble. The alkali metals are always soluble. So now all we need to do is balance the reaction. So notice that we have 2 chlorine atoms on the left side. Therefore, we need to put a 2 in front of NaCl. And we have 2 bromine atoms on the right side, so we need a 2 in front on the left side on NaBr. So now it's balanced. So now we can write the total ionic equation. So chlorine, which is a gas, we're going to leave it the way it is. Sodium bromide is in the aqueous phase, so we're going to separate those into ions. Now we can do the same for sodium chloride. We we can write it as 2Na plus and 2Cl minus. And bromine, which is a liquid, is going to remain as Br2. So the only spectator ion that we have is the sodium cation. So the net ionic equation is going to be Cl2 gas plus 2Br minus, which is going to produce 2Cl minus, and bromine liquid. And all of the ions are in the aqueous phase. So let's write AQ. And so that's it for this particular single replacement reaction. That's how you can balance it. Now, for the sake of practice, let's try one more double replacement precipitation reaction. So let's say if we have an aqueous solution of calcium nitrate, nitrates are always soluble, and if we mix that with sodium phosphate, and as you know, sodium is always soluble. So feel free to pause the video, predict the products, and balance the equation, and write the net ionic equation as well. So when Na pair up with NO3, these two have the same charges, so they're going to pair up in a 1-to-1 ratio. So it's simply going to be NaNO3, which we know it's going to be soluble. Nitrates are always soluble. Now, if we pair up calcium with phosphate, calcium has a +2 charge. It's an alkaline earth metal. And phosphate, based on your polyatomic ion sheet, if you don't have one, look one up in Google Images. It's phosphate, it's PO4 3-. So to write the formula, it's Ca3PO4 with a 2 in front. And hopefully I can fit it in here. And phosphates are generally insoluble. The exceptions are the alkaline metals, and calcium is not one of them. So this is a solid. Anytime you mix two aqueous solutions, and if you get a solid, it's a precipitation reaction. So now go ahead and balance the precipitation reaction. So notice that we have two phosphate ions on the right side. So we need to put a 2 in front of Na3PO4. And we have 3 calcium atoms on the right. So we need a 3 in front of CaNO3 2. And notice that we have 6 nitrates. 3 times 2 is 6. So we need a 6 in front of NaNO3. So now let's write the total ionic equation. So we have 3 calcium 2+ ions in calcium nitrate, and we have 6 nitrate ions. In sodium phosphate, we have 6 Na+ ions, and we have 2 phosphate ions. On the right side, in 6 NaNO3, we have 6 Na+ ions and 6 nitrate ions. Now, calcium phosphate is a solid, so we're going to write it the exact same way as Ca3PO4 2S. Everything else is in the aqueous phase. So the spectator ions are nitrate and sodium. So for the net ionic equation, it's going to be 3Ca 2+ aqueous plus 2 phosphate ions aqueous, and this is going to yield solid Ca3PO4 2, and that's it. That's the net ionic equation. So that is it for this video. Thanks for watching, and I really hope that you have a better understanding of how to write net ionic equations.